Okay, and the next presenter is Federico Mora, which is going to talk to us about message change for distributed system verification. Please.
Awesome. Can you hear me? Yeah. Okay, cool. Okay, so thank you everyone for coming. So I'm just going to get right into it. It turns out that it's not very hard to find examples of bugs in important distributed systems. So here's one that I found in a blog post that I particularly enjoyed. This is a senior principal engineer at Amazon Web Services just describing how a bug in an implementation brought down all of Amazon.com. It's a fun read. I definitely recommend it. The point that it gets across, especially for this presentation, is that distributed systems have bugs. These bugs exist in real systems. They're common and severe. Okay, so luckily we have some tools at our disposal to try and help with this. So the kind of tools that I'm particularly interested in are formal verification systems. So on the screen you see kind of like a sketch of what the usual input-output behavior of these tools is. So on the left you have like a system description S, some properties usually in the form of invariance I. Then these are given to a tool which is in the middle that checks or tries to prove that S satisfies I. Ideally, you get a check mark and you're happy you're done. Most likely what you get is kind of like a timeout or an unknown or a counterexample to induction, and you have to like fix your system S or update your invariance or something like that. And one kind of rule of thumb that's important for this presentation in the space is that usually like the more detailed your system S gets, the harder it is to get your invariance I right to get that proof to pass. And so this is an issue for us because the goal for our work for this presentation is to try and verify asynchronous distributed systems kind of like as close to the implementation level as possible. So specifically, we want to basically verify systems that look like what a developer would write in a language like Erlang or P or using a library like Akka. And so these languages are explicitly talking about message passing using this concept of like an event handler, which I've pasted 3 examples on the screen. These are like blocks of code that describe how a process reacts to an incoming message. This will become relevant later, but this is kind of like what we're trying to target with this verification. Okay, so overall the contributions that we're going to make in this paper is we're going to define message chains, a notion that we're then going to use to verify asynchronous message passing systems while avoiding reasoning about individual messages or individual buffers and without having to like manually abstract your system too much and without having to like manually relate these abstractions back down to your implementation level. We're going to do this all in a prototype tool called the UpVerifier that targets like a P-like language. That's where the P from UpVerifier comes from. Okay, so to make it a bit more concrete, we're going to look at an example. This is from a publication from 1979 that I'll just call the Chang and Roberts algorithm. It's a really nice paper. They have, I'm going to pull out basically 2 paragraphs that summarize the algorithm really well. So we can kind of get rid of a little bit of noise here. Essentially, what you have is a circular arrangement of nodes. They can communicate clockwise, and what they're trying to do is collectively collaborate to figure out which one of these nodes has the largest ID. They also have unique IDs, by the way. Okay, so the code, the description for the algorithm is, again, really simple. We're going to skip through this quickly. Essentially, each node will start by sending their ID clockwise, and then the nodes will be receiving these messages. If the message they receive is larger than their ID, then they're going to forward that. If the message they receive is less than their ID, then they're going to kind of ignore that. And if they receive an ID that's equal to their own, then they're going to realize that they're the leader, that they should go do the thing that they want. So here's a really extremely rational instance of the Chang and Roberts algorithm that you can use for your next OOPSLA submission. So if you have to maybe draft a rebuttal or something like that, you need to pick one of your co-authors to open that document, start drafting the rebuttal. You can use the Chang and Roberts algorithm. Basically, you would have your orc IDs as the unique IDs. You would have the author list give you that circular arrangement, and you can use email for message passing. This is kind of a joke, but I'm going to use it as an analogy for message chains later on. Okay. Oh, and by the way, the goal would be the specifications that you would care about here is like you don't want 2 authors to think that they're the leader and start kind of like drafting a rebuttal. That would be bad. Okay. So let's try to model this system, and let's try to verify it later. Since this system has been around since more than 40 years, basically everyone has verified it. And so here is an example in TLA+. It's a little bit hard to read, so you might have to just take my word for it. But essentially what they're doing is they're defining this messages variable, which is like a global shared variable, and they're modeling message passing using that variable, kind of in like first order logic. This is really common, so this is a more recent tool called mypyvi. This, I should mention, is zoomed into the code that's actually like receiving a message and deciding what to do in that protocol. And so the proof in mypyvi is essentially the same as the TLA+ one. Instead of a messages variable, we have a variable called pending, and they're doing kind of interesting things, like for example, when a node actually receives a message, it doesn't necessarily kind of like mark it as received. It could just like continuously receive the same message over again. And that's fine, it works for the proof, it's an abstraction. They're manually modeling message passing. Okay, and of course there are many more choices. There's stuff like Ivy in the domain-specific tools space. There's also proof assistants, there's software verification engines. In general, what you see when you go out and look at proofs for this protocol and protocols in general, it's that, people are manually modeling message passing, and then they're writing proofs about these kind of like shared memory variables, these abstractions. Okay, so what we want to do and what the up verifier does is it actually takes P-like code, and so it takes message passing kind of like event handlers like this, and we want to verify at this level. So this leads to kind of like shorter code for the engineer or formal verification user, but it's also can be a little bit dangerous because it's more detailed in the semantics of message passing. Like we don't have those abstractions to play with. We're actually at the message passing level. And so as we know from our rule of thumb, the more kind of detailed your system gets, the more work you have to do at the invariant level. Okay, and so that's where our main contribution is. This is where we're going to go on a little bit of a tangent to define what message chains are, and then we're going to return to that system and verify it using message chains and see why that's really cool. Okay, so message chains, first of all, they're just like a data type, and it looks almost like a list data type in a functional programming language. So message chains are either empty or they're kind of like this send object, where a send has a source, a target, a payload, and then this kind of like this history, which itself is a message chain. And then the semantics of the message chains, how we like create these, is basically like our verification engine will automatically instrument the P code following two rules. So first, if you have a send statement that's like inside of an event handler, then what we do is we like extend the message chain that we received. So we'd be receiving a message chain, and then whenever we have a send, it's like that message chain that we received is like the history of the new one. And then the second case is even simpler. If we're sending a message outside of a event handler, then the history is just empty. So if you remember our rebuttal election example, case 2, where we're kind of like sending from scratch, is on the far left. It's just that first email in an email chain, and then there's the email chain on the far right is like successive applications of case 1. Like we're extending these message chains. Okay. And then finally, when I talk about message chain invariance, essentially I just mean like a predicate P that holds for all message chains that appear in the system. And so everything is fixed, and P is just the predicate that kind of talks about the message chains. So again, in the rebuttal election example, a couple message chain invariants that are sort of interesting is that if you look at any of these emails, the most recent email always holds that largest ORC ID. That's like a useful property, interesting property. Another one is that we never skip an author, like we're always going in that circular arrangement. All right, cool. So now we actually have everything we need to do a full verification of the Cheng and Roberts algorithm. And so here it is. This is kind of heavily commented, but with invariance directly from the proof. So the properties that we care about are at the top. They're basically just saying that we want at most one leader to be elected, and we want that leader to be the one with the largest ID. So these are safety properties. And if we were to give this to our tool, we would essentially get a counterexample to induction. Like alone, they're not enough to prove, they're not inductive. So what we can do is we can add 2 message chain invariants, which are exactly what we already saw. So we want to say that the largest ID at the front of every message chain is, or the ID at the front of every message chain is the largest ID in that message chain. And 2, that we never skip anyone. We never skip an author in that order. And so that one's a little bit harder to write, but it's described there as well. And so this is really cool, actually, because that proof, first of all, it guarantees that the system works no matter how many nodes are in the system. So it's kind of like parametric in that sense, which is cool, but other people are already doing that. What's even kind of like extra cool is that the proof never once talked about like individual messages. It never talked about like individual message buffers. It didn't require any kind of like abstractions, manual abstractions. And the automated abstraction that we put in, this message chain one, was kind of like automatically related to the implementation level detail. And also I would argue that the invariants were relatively intuitive. So that's yeah, we're really excited about this. What's kind of maybe even more exciting, especially moving into the future, is that we can learn a lot of these message chain invariants automatically. And so just we're using techniques called specification mining. Quick definition here is that specification mining is a machine learning approach to discovering formal specifications that code likely obeys. So it's kind of like you're giving observations as input, and the tool is giving you back like a predicate that should hold for those observations. In our setting, we're interested in learning message chain invariants. And so kind of more concretely, like we can take a tool like Trio, which I've cited on the bottom here, which is a program synthesis tool for recursive functions. We can give it example message chains that occur in the system. Just we can generate those by fuzzing the system. We can give it some hints of message chains that don't occur in the system, shouldn't occur in the system. And it will automatically synthesize a recursive function, like lightning quick. It's a really impressive tool that is equivalent to the first auxiliary invariant that we used. And this is just from examples. Another way to think about it is like we're kind of giving this tool like a bunch of emails from our rebuttal election, and it is returning like, hey, the most recent email holds that largest orc ID, which is a property that we used for our proof. Okay, so sorry, that was a bit of a whirlwind. And so let's kind of step back a little bit and try to talk about an evaluation. So in the paper, we go over 5 research questions, and I encourage you to go check them out. For the presentation, I'm only going to talk about RQ2 and RQ5. We mentioned a little bit of RQ3. So in the paper, we basically look at more case studies, kind of like the Chang and Roberts verification, and we show what the proofs would look like using message chains. We also do the same thing for specification mining. Yeah, and so definitely check that out in the paper. The RQ2 is, RQ2 tries to answer like it's a performance comparison. So essentially, we have our compiler that is automatically instrumenting all these message chains. It's adding new variables. It's doing some work. And so one thing that you might be worried is that we're getting a really big performance degradation. And so what we did to evaluate that is we essentially took a bunch of benchmarks from a PLDI 20 paper from MyPyVi. We translated them to the up verifier kind of like as faithfully as we could. And then we timed the verification. And we found that there doesn't seem to be that big of a performance degradation, if at all, when using all our kind of like compiling infrastructure and verification. So that's exciting. We then also took 2 systems that were kind of relevant to one of our co-authors, Ankush, who works at Amazon Web Services. And so Amazon Web Services had a couple systems that they were interested in verifying. We talk a little bit about this in the paper. The first one, Global Clock, is kind of a smaller system. It takes about 1.5 seconds to verify. The second one, I think, is a little bit more interesting, so I want to take a second to talk about that. It's a 2-phase commit multi-version concurrency control protocol. And one kind of exciting thing here is that in two-phase commit, you have this kind of like this situation where you're sending out, you're broadcasting a lot of messages, and then you're kind of like waiting for responses. You're sort of like flooding. And so message chains are a very linear thing, so it's kind of surprising that even though we have this non-linear kind of artifact, that they're still useful. And so I'm out of time, but thank you everyone for listening, and I'm happy to take any questions that you might have.
Okay, we have a couple of minutes for questions while Leven sets up.
So on your slide 31, you have this property. No worries.
Okay.
That, you guarantee that at most one drafts the response. What about at least one drafts the response? So you have safety, but what about liveness?
Yeah, that's a good question. We don't do any liveness. We're in a purely asynchronous setting, so liveness kind of goes out the window. We're kind of thinking about starting to support like partial synchrony and situations where we can start getting some liveness back. But our system model doesn't, like, we have no kind of guarantees that a message will even eventually get delivered. So no liveness for now.
So actually, what is the system model? Because you are doing an abstraction over a message that is sent over a channel. So what are you assuming from the channels?
Very little. So we're like purely asynchronous message passing system. We're assuming that there's no kind of like scrambling, like on purpose, whatever. But since we're doing like our proofs by induction, kind of like the solver is free to explore kind of like crazy states before, like pre-states before our inductive step. We're able to kind of like put something into the network, and we're able to grab from the network.
Eventually arrives no disorder.
Oh no, there's no order.
Okay.
It's asynchronous. Yeah.
Okay, thank you.